Unit 1 Chemistry, Part 3. We are looking at evidence for electron shells and other atomic models. So, we looked in the last video at the fact that we believe electrons orbit the nucleus in shells, not just in a random pattern. The evidence for that is here. Okay? Now, these are what we call emission spectra. Each of these black ones here, are for a different element. These are produced when we do something like a flame test. So we excite an atom by giving it lots of heat. And that makes the electrons get more energy. And when they get more energy, they move to a higher energy level, or a shell which is further out. When they get there, that's unstable, so they're going to fall back down towards their ground state. The ground state is their normal place where they like to be. And when that happens, they give out light, because light is a type of energy. So what we see here are different wavelengths which correspond to different amounts of energy. So if we take that light that's emitted and we split it up in a spectrum, just like we can split up white light with a spectrum by putting it through a prism, and you'd get a rainbow. Here, we can split up this light by putting it through a prism, and we get this thing called an emission spectrum. Okay? Now, what's actually going on? You would see an electron, which is in its ground state, lowest energy level. What we're going to do, give it some energy, that's going to make it go up to an excited level. We don't know how excited it's going to get, but it's going to get excited. It's going to go, yay, and bounce up. But being up in that excited level is unstable. It's not happy up there. So it's going to fall back down towards ground state. Okay? It may fall all the way, so it could fall from here down to ground state. It could fall just that little bit. It could fall, as in this example, from N4 down to N2. The difference between them is a difference in energy level, and that energy is going to correspond to a specific wavelength of light. If it got excited and went all the way up to N4 but then fell down only as far as N3, it's going to release less energy, which is going to give you a light which is a different colour. In this case, it's going to give you a light which is more red. Okay, if we think about the visible light, red is the lowest energy and purple is the highest energy. Now, one more thing on that. You're not going to be expected to look at spectra and work out what the shell arrangement is. Just accept that this is where the spectra come from and that this is evidence for the fact that shells do exist. The other model of the atom that you need to consider, kind of side by side with Bohr's one, is that electrons exist as particles, but they also in many ways behave like waves. If you want to really think about how waves behave, take physics, okay, because you'll do a lot of studying of waves. But waves can basically be in many places at once, yeah? So we actually picture electrons as clouds of negative charge rather than distinct entities, rather than particles. And with mathematical modelling, we can figure out the likelihood of an electron being in a given location at any one time. And basically, they're more likely to be where the shells are and less likely to be in any other place. The benefit of this, partly it better explains behaviour, partly it allows the electrons to accommodate 3D space at once. So it means that we don't see gaps in matter. It is constant matter. The other thing that Schrödinger's model explains is the division of shells into subshells, which will be covered in the next video.